Hello, it's me again. In the previous videos in this series, we have seen that electricity is energy that can be measured using instruments. We now understand that Gibbs free energy is a scientific theory that proves that free energy immediately fills any void. And I demonstrated this by saying, when I take this glass out of the bigger glass, there is no hole in the water. This is due to gravity, which is a form of energy, which is making the water surface level. Confusion arises from the fact that for every force there is an equal and opposite force, but this does not mean that there is a negative force. It means there is another force going in the opposite direction. As you can see, I lift this ball against gravity. The force of gravity causes the ball to drop, which transfers the energy into this ball, which goes up to a level, and gravity forces it to come back down again. So this is a demonstration of every force having an equal and opposite force. This is called Newton's cradle. There is no such thing as zero energy, but there is a zero on all meters because we are making comparative measurements, and zero will appear on the display if there is exact equality between the two inputs of the meter. In this meter I have arranged it. The black is in the common, the red is in the measuring one, and I have put a copper wire in which there's no energy between the two inputs of the meter. When I switch it on to volts, which is a potential difference measurement, you will see that there is zero on the meter. This is because there is no potential difference between the common and the measuring input. If, however, we put a dry cell battery between the two ports of the meter, like this, we will then, when we switch on the meter, we will see a measurement which is in volts, which is a potential difference. This is 1.11 volts. That means that the potential between this end of the battery and that end of the battery is 1.11 volts. So the potential here might be considered to be zero, which is common, and the potential here is 1.11 volts. This electromotive force is caused by the acid in the battery reacting to the metal shell of the battery, so it is a corrosion reaction that is causing this energy release, which makes the reading on the meter. Early corrosion engineers put a piece of copper in a saturated solution of copper sulfate. This is copper sulfate in here, and they called it a half cell. They put this on the ground in order to get a voltage measurement that they called the pipe to soil potential. They called the copper in saturated solution of copper sulfate a half cell, and that's wrong. It's not a half cell, it's just an electrode. They said that a reading of negative 0.850 volts indicated that the pipeline would not corrode. However, pipelines continued to leak when the value of negative 850 volts was obtained. Some people tried applying a shift of 300 millivolts from what they described as the natural potential, but still pipelines leaked when they met this criterion. Others said that a shift of 100 millivolts would do the trick. If this was taken, immediately the cathodic protection system had been switched off. I recognise that the basic error is in the measuring procedure itself. I was told that copper in a saturated solution of copper sulfate has a known potential. This is not true. It varies with temperature. Copper sulfate is produced by dissolving copper metal in hot concentrated sulfuric acid. Copper wire has to be pure because this determines the conductivity, so we can strip some wire for our experiments. We can also buy copper rods if we want to, like I've bought here, and they are made to the specification that is required. We can put the copper sulfate solution in any non-conductive container and use any material that is absorbent, that is a piece of wood, like I've used here. This is a piece of wood. It absorbs the copper sulfate, and therefore when we connect to the piece of wood it makes an electrolytic contact, a contact with the electrolyte in here, and the copper completes the circuit, so we have now an electrode which we can measure the potential of this electrode. So I will switch this on and you will see that we have a voltage which is changing. It's not stable, and you will watch as this reading changes. It is reducing from 0.360 and it is now down to 45 millivolts, still reducing, and now it goes into the negative, and it is building up in the negative. So there is a complete change in the reaction within this electrode, and the change can be due to many features. It might be the temperature, it might be ultraviolet light, it could be many things, but this is not a stable potential as required in cathodic protection measurements. It is not a half cell and it is not a stable potential.